Hello dear students, welcome to my YouTube channel. This is Joginder Rohila, and in this video I am going to discuss with you factors affecting the magnitude of crystal field splitting. In my last video I have discussed with you about crystal field splitting in square planar complexes. I also have discussed with you crystal field splitting in octahedral and tetrahedral complexes. Now I am going to discuss with you the main factors which are responsible for crystal field splitting. Okay, the first factor is the nature of ligands. The nature of ligands. The nature of the ligands. When in a particular complex, metal ion is surrounded by a number of ligands, and if the ligand is negatively charged, the more is the negative charge and the small is the size of the ligand, greater will be the value of crystal field splitting. More negative charge, small size. It means if a small sized ligand is there, that can easily interact with the metal ion, that can effectively interact with the metal ion, and crystal field splitting will be high. And if in case of neutral molecules, suppose if neutral molecules are the ligands, in some cases the ligand with more basic nature and the ligand with more polar character, that will show greater crystal field splitting. If you see a particular series which is present over here, this series is called spectrochemical series. In this series, ligands are arranged on the basis of increasing crystal field splitting. It means the ligands which are present on right hand side, these are called strong field ligands. These are having greater crystal field splitting, and these ligands which are present on left hand side, these are having low crystal field splitting. These are called weak field ligands. Okay, I have discussed with you the crystal field splitting depends on the nature of the ligands. The ligands with more negative charge and small size, that will be showing more crystal field splitting, or you can say the ligands which are having high charge density, that will show greater crystal field splitting. If you compare this concept with halides, if you compare with iodide with bromide, bromide with chloride, and with fluoride, the small sized fluoride with the same negative charge, it means that is having high charge density, that fluoride ion will show greater crystal field splitting. So in comparison to iodide, bromide is having greater crystal field splitting. In comparison to bromide, chloride will have greater crystal field splitting, and fluoride will have greater crystal field splitting. Similarly, if you compare water molecule with ammonia, ammonia is more basic in nature. The neutral molecule which is more basic in nature, that will show greater crystal field splitting. So dear students, you can compare the ligands on the basis of crystal field splitting with this spectrochemical series, and this spectrochemical series is designed on the basis if these ligands interact with the same metal ion in the same oxidation state and in same geometry, only then we can compare the crystal field splitting for these ligands. So the first factor on which crystal field splitting depends is the nature of the ligands. Now I am going to discuss with you the second factor on which crystal field splitting depends, that is oxidation state of the metal ion. Okay, second factor on which crystal field splitting depends is the oxidation state of metal ion. The central metal ion with more oxidation state will show greater crystal field splitting. If I discuss with you a particular series, the cases of particular series, suppose if I discuss with you the cases of first transition series, like if cobalt is present in +3 oxidation state, if it form a complex like CONH3 3 positive, and if cobalt 2 positive form a complex like suppose if I compare the two complexes of first transition series, cobalt with ammonia, and in this complex cobalt is present in +2 oxidation state. Cobalt is the member of first transition series. In first complex it is present in +3 oxidation state. In this complex it is present in second oxidation state. Both the complexes are of octahedral nature, but based on oxidation state, crystal field splitting in this case, in which cobalt is present in +3 oxidation state, that is having higher crystal field splitting in comparison to cobalt in +2 oxidation state. As a result, this complex is called a low spin complex. A low spin complex, or you can say this complex is diamagnetic in nature due to this higher crystal field splitting. And in this complex is called a high spin complex. High spin complex. And this complex is paramagnetic in nature. Paramagnetic in nature, because if crystal field splitting is large, then what will happen? Electron will prefer to pair up in the lower energy level. If electron will prefer to pair up in the lower energy level, number of unpaired electrons will be less. The complex will be less paramagnetic, or that can be diamagnetic in some cases. And the cases in which crystal field splitting gap is less, electron prefers to go to higher energy level. In that case, number of unpaired electrons will be higher. So the system with more paramagnetism can be there. So in a particular oxidation state, if metal ion is present in higher oxidation state, that will show higher or greater crystal field splitting. And this type of crystal field splitting can be around 1.5 to 2 times higher than the metal ions in the lower oxidation state. If I take another example of this first transition series, if I take the example of iron, if iron form complex with water molecules in +3 oxidation state, the magnitude of crystal field splitting in this case is 13,400 per centimeter. If the iron of first transition series in +2 oxidation state forms complex with water, and there is another complex of water, that is FeH2O6 2 positive, and in this case, what is the magnitude of crystal field splitting? That is less. That is around, you can say, 10,400. You can see exact values in the book, but that is around this. That is around 10,000 per centimeter. That is around 13,400 or 700 something. So I mean to say that in a same transition series, if a metal is present in higher oxidation state, that will show greater crystal field splitting in comparison to the same metal in lower oxidation state when it forms the complex of same nature and with same type of ligands. So this is the another parameter on which crystal field splitting depends. And what can be the reason? Can you tell me what can be the reason that a particular metal ion in higher oxidation state shows greater crystal field splitting? You can easily understand, if a metal is present in higher oxidation state, that will be of lower size. If that will be of lower size and oxidation state is large, it means that is also having higher charge density. If high charge density, small size species is there, it means the interaction with the ligands is very effective and the crystal field splitting will be large. Okay, now I am going to discuss with you another important parameter on which crystal field splitting depends. That is type of, the third parameter is types of d-orbitals. Types of d-orbitals. It means the d-orbitals in which electrons are present, or the metal ion which is participating in complex formation. In that metal, which type of d is there? Suppose if you compare the cases of 3d orbitals, if a metal in which electron is present in 3d orbital, and another metal in which electron is present in 4d orbital, and another metal in which electrons are present in 5d. If you compare the magnitude of crystal field splitting will be higher if the electrons are present in higher d orbitals. So in these cases, 5d orbitals, metal ions with 5d electrons are showing greater crystal field splitting in comparison to 4d. 4d will show greater crystal field splitting in comparison to 3d, and this type of magnitude can be 40 to 50% from one case to another case. You can say if a particular metal ion of lower transition series form a complex, and in comparison to this, the metal ion of the same group, or it means the metal ion of the higher transition series that make the complex, the crystal field splitting for higher transition series will be high. Let's discuss this type of example in a very effective manner. We'll take the example of cobalt in +3 oxidation state. Suppose CONH363 positive. This is the complex formed by cobalt in +3 oxidation state. Cobalt is the member of first transition series, 27 atomic number. Okay. In this case, suppose the crystal field splitting. So crystal field splitting, suppose if I want to discuss with you, that is around 24,000 per centimeter. For example, this is like this, around 24,000. Suppose this is around 24,000. And cobalt, the next member of this group, rhodium, also forms a complex with ammonia in +3 oxidation state. Why I have discussed rhodium with ammonia? Because cobalt is present in first transition series, and below cobalt there is rhodium. Rhodium atomic number 45. It forms the complex in +3 oxidation state. In this case, electrons are present in 3d. In this case, electrons are present in 4d because it is the member of second transition series. In this case, if you compare, its crystal field splitting is around, you can say that is around 34, or you can say that is around 35. So this is around 35,000 per centimeter. It means, I mean to say, crystal field splitting is large. You can see exact values of these crystal field splitting in your book. Okay. The next member, if you compare these two complexes with higher transition series. Okay. If I want to show you the complex of iridium, and this is having more value of crystal field splitting, suppose that is around 41,000 per centimeter. I am taking these values around the exact values. These may not be exact values, but their behavior to increase from one metal ions in a particular d orbitals, and the another metal with some higher d orbitals, another metal with higher d orbitals. You can take the comparison between these three. Okay, cobalt 27 atomic number, electron is present in 3d. Rhodium 45 atomic number, member of second transition series, it is having 4d electronic configuration. So electrons are present in 4d. Iridium 77 atomic number, member of third transition series, electrons are present in 5d orbitals. So when we go from 3d to 4d to 5d, if 5d is present in complex formation, that will show greater crystal field splitting. If same geometry is there, same oxidation number is there, with same ligand the complexes are formed. So this is the third type of parameters on which crystal field splitting depends. Okay, I am going to discuss with you another parameter. This is very important, and we have already discussed with you about this parameter. That is the next parameter is fourth parameter, geometry of the complex. Geometry of the complex. Geometry of the complex. I have discussed with you that crystal field splitting in case of octahedral complexes are higher in comparison to crystal field splitting in tetrahedral complexes. And tetrahedral complexes, crystal field splitting is 4/9 of octahedral crystal field splitting. Can you tell me why it is so? Why in case of tetrahedral complexes crystal field splitting is less? Dear students, we have already discussed why crystal field splitting is less in case of tetrahedral complexes in comparison to octahedral complexes. Just remember, In case of tetrahedral complexes, there are 4 ligands, but in case of octahedral complexes, there are 6 ligands. So magnitude of crystal field splitting in case of octahedral complexes will be large in comparison to tetrahedral complexes. Moreover, in case of octahedral complexes, some of the interactions are on principal axes. But remember, no interaction is on principal axis in case of tetrahedral complexes. Therefore, crystal field splitting is less in case of tetrahedral complexes in comparison to octahedral complexes. And the magnitude of crystal field splitting is like this, delta T, which is crystal field splitting in tetrahedral complexes. This delta T is 4/9 of octahedral crystal field splitting in octahedral complexes. So these are some of the parameters on which crystal field splitting depends. First parameter was nature of the ligand. Second parameter was oxidation state of the metal. Third parameter was types of d orbitals in which electrons are there. Fourth parameter is geometry of the complex. Dear students, prepare this question. This is one of the most important questions regarding exam point of view. In most of the cases, most of the times, this question is repeated again and again. And so many things are dependent on these parameters. Please try to prepare this question. This is very important topic. Factors affecting crystal field splitting. Okay, dear students, we have discussed in this video factors affecting the crystal field splitting. In our next video, I will be there with some more interesting examples, more important questions regarding exam point of view. And if you like the video, please share this video. And please subscribe the channel and keep watching, keep learning. Best wishes. Thank you so much.